So hi guys. So our next meeting is going to be on next Thursday. And then whatever we cover until Thursday will be a fair game on next midterm. So before we start, any questions so far? Okay, I think we might just get started. So today we are going to talk about the chi-square test. So a chi-square test is different from what we learned in the past like 3 weeks. In the past 3 weeks, we learned about the z-test, which is used to do a proportional test and also do a proportional confidence interval. And also t-test, which do a proportional confidence interval on mean and also on significant tests for mean. And now we are going to learn another distribution, which is a chi distribution. It's asks you to do a significance test for multiple proportions. So we do a one sample z significance test, only analyze the proportion for one category. And then two proportion z significance tests can only analyze the difference in proportions for two categories. But what happens if we have more than two? Then we need the chi-square test for more categories. And then for chi-square test, we have three kinds. The first kind is the goodness of fit. The second kind is the test for homogeneous. And the third type is the association for independency. And then for the first one, the chi-square goodness of fit test, we test one variables and analyze its distributions. Among all of the categories. And then it compares the expected distribution to the actual one and see if your expected distribution is the same as the actual one, or you have a difference in distributions. Compare counts and not proportions. And just remember, for this test, we compare the counts, but not the proportions. And then the test for homogeneous is to analyze the distributions, but now we are checking if the distribution is the same or different. For several populations or treatments. And then the last type is the chi-square test for association, which means we want to see the sample or experiment from a single population and break them up around multiple variables. And we then check to see if there is an association between those variables. So those are the three tests we are going to go over for this week. So test for chi-square in this course. And then the chi-square distributions. So let's first introduce what a chi-square distribution means. The chi-square distribution is a distribution that measure of the distance of the observed count, like the one that actually happened, from the expected counts. This is the one that should happen. And in that case, we can compare the two distributions and see if they actually have the same distributions or not. And unlike a normal distribution or a t-distribution, the chi-square distribution is not symmetrical. And the chi-square of distribution does change based on the number of categories, creating a degree of freedom. So on the t-distribution, the distribution itself will be affected by the number of degree of freedom that we have. So same thing for chi-square. It's going to be affected by the degree of freedom. And then the followings are the characteristics of being chi-square. And then you can see this is the distribution for chi-square with a degree of freedom of 4. And this is the degree of freedom of 8. And this is the degree of freedom of 1. And then as you can see, the distribution is right skewed with only positive values. And then as degree of freedom becomes larger, it becomes less skewed. And as the degree of freedom becomes larger, larger values become more probable. So a higher p-value, which means it's harder to reject our H0. So remember that our type 1 error is the alpha, which is set by the significance level. So we have we have like fully control on that. And the second error, which is the type 2 error, which is we have no control on, but always we want to make the type 2 error as small as possible. So now for more degree of freedom, the larger values become more probable, which means a higher p-value, which means it's harder to reject H0, and again, which means lower power and higher type 2 error. This too means the distribution is less accurate for a higher of degree of freedom. So this is different from our t distribution, because remember when t distribution has a higher degree of freedom, the distribution is more like a normal. So compared to a t distribution, this is the normal distribution Z. And this is the t distribution with degree of freedom maybe like 10. And as the degree of freedom increase, and this is the t distribution with degree of freedom equals 20. So for t distribution, as our degree of freedom increase, our p-value decrease, which means it's easier to reject our H0. And also means the power is higher. And the type 2 error is lower. So it means more accurate. So we can see these two distributions are opposite. So for t distribution, if our degree of freedom is higher, that means it's more accurate. But for for chi distribution, if our degree of freedom is higher, that means less accurate. So that's the main differences between a t distribution and a chi-square distribution. And then the mode for the chi-square distribution will be at the degree of freedom -2. So that is just a definition. So there's no y behind it. And the mean is the same as the degree of freedom. So let's say for the degree of freedom of 8, for this distribution here, you can see that the peak is at here. And then for this distribution here, the degree of freedom is 8. So the peak is 8 minus 2, which is 6. See? These two numbers matches each other. So this is how you can like roughly sketch your chi-square distributions. And the variance for chi-square distribution is 2 times of degree of freedom. So you can see that if the degree of freedom is higher, then that means you are more variate, means less accurate again. And then the chi-square is the summation of observed minus expected square over expected. And this is the chi-square statistic. And then again, before we can do any like test, we need to check if the conditions satisfy for chi-square distributions. So for chi-square distribution, you have 2 conditions, which is a large sample and also independency. So for large samples, we require that all expected values are greater than or equal to 5. That is the condition for large samples. And it is okay if our expected counts are in decimal points. And then for independency, again, is make a reasonable assumption that our population size is greater than 10 times of the sample size. So this is the 2 conditions we need to check for a chi-square test. Okay, then now let's move on. So now the first test. We are going to talk about is the chi-square goodness of fit test. So again, the chi-square statistic is the summation of observed minus expected over expected. And then calculate a p-value with the lower bound and upper bound with degree of freedom is the number of categories minus 1. That is the degree of freedom. And then compare the p-value to the significance level alpha. And then if your p-value is less than alpha, that means we can reject our H0. And if p-value is not less than alpha, we fail to reject our H0. We reject H0, so we have convincing evidence for HA. But if we fail to reject H0, that means we do not have convincing evidence for HA. So the rule for reject and fail to reject are the same. But only the test statistics are different now. So any questions? Okay, so let's move on. Let's look at this example here. So now we want to see that if like the age distribution of people who answer the telephone surveys is not the same as the age distribution of all US residents. So this is our like hypothesis question. So now we just want to see that our P2, which is the probability, the proportion of the 20, like age of 20 to 29, which is 19.1%. And the 30th is 21.5%. So we are trying to see the 30th group is 0.215. And also P4 is, and P5 is the 50. And the P6 is the 60. And then our alternate hypothesis is that at least one of the PI is incorrect. So this is a test for goodness of it. So it's asking if my samples follow like a certain distribution. So that is a goodness of fit test. And then now let's check the conditions. So we need to check two conditions. One is a large sample. So we need to make sure all the expected counts are greater than 5. So how to find the expected counts? So this is our observed counts. This is the observed, and the expected is going to be the total 1048 times the expected distribution. So those are the expected counts for our 5 categories. 5. So the first one is 200.168. And the next one is 225.32. That's 221.128. $162.44. 238.944. So those are the expected counts that we should use. And then we can see that all expected counts are greater than or equals to 5. So the large sample conditions satisfy. And also independency. So just make a reasonable assumption that there is more than like 10,000 like residents in the US. Reasonable to assume there is more than 10 times of the sample size in the US. And now is to find the chi-square statistic. So a chi-square here is the summation of observed minus expected, and then take the square of it, and then all over expected. So what does that mean is that those are our observed counts, and those are our expected counts. So we can do 141 minus 200.168. The line is too long. And then square over the expected. Plus so this is how you find your chi-square test statistic. Like adding those numbers all up. So take a minute to do the math. So the answer would be 48.172 after you do all the math. And now let's learn how to find a p-value using this. So take out your calculator. There is a way to do it on calculator, but it's only work for TI-84, not for the other one. So let's say you feel like the entire process is too long, and then you are trying to do it on your calculator. Yes, there is a way to do it on calculator, but it's only work for TI-84. So if you have like a TI-36, then I'm sorry, it's not going to work on there. So go to stat, go to edit, and then put in all your number. And then now go to stat, go to test, and there is a chi-square goodness of fit test. And then just on L1, that is your observed data, and then they will put your expected on your L2. And then the degree of freedom is 5 minus 1, which is 4. Oh, wait a second. Here is 5. Yep. Wait a second. Okay, wait a second. Go to L2 and put all the expected counts there. Maybe, oh yeah, because they do not know what your expected counts is. So put all your expected counts there. Yeah, put all your expected counts on L2. And then go back to the home screen. And then now go to stat, go to test, and go to chi-square goodness of fit. And then here is 4. Now it is. So the chi-square is 199.6.12. Oh, I did my math wrong somehow. So this, the chi-square here is the summation of all the observed minus expected square over expected. And then the P here means the P value. So our P value in this case is 0. And how to use your calculator to get the P value is by using a second bars, go to distribution, and then go to chi-square CDF. And then our lower bound is 199.6.92, and the upper bound is infinity. Degree of freedom is 5 minus 1, which is 4. So this is our chi-square p-value. Any questions? So now since our p-value is less than 0.05, which is our significance level, and we can reject the new hypothesis, and then we do have convincing evidence that at least one of the proportions in the age group is not the same as the age distribution of the US residents. Questions?
For the chi-squared, I had gotten 48.172.
Oh yeah, that's weird because the first time I got 48. So I thought I made a mistake on that. Let me double check. Yeah, you're right. It's 48. I misput the expected values. Yep. It's 48. Yeah, this is what I got for the first time. And then the p-value this time is also very small, so our conclusion doesn't change.
Sorry, and for the p-value, it's x squared CDF, and then we use the 48.172 for the lower bound.
Yes. So the p-value is chi-square CDF from 48.172 to upper bound infinity, and the degree of freedom is 5 minus 1. And then let's say you don't have the TI-84, then what should you do? So the second approach, with no calculator. So if you don't have a calculator, then you need to input those like gigantic equations by yourself and calculate the values. Which is 48.172. So you need to do this number, like really like enter it to your calculator one by one. And then after you get this, the second step is to find a critical value. And because we know our significance test has a significance level of 5%. So let's go to a chi-square distribution table. So we have a significance level of 5%, which is this column here. And then our degree of freedom is 4. So the critical values we have is 9.49. What the number is? I have very bad memories now. And definitely our chi-square statistic is greater than the critical value. So that's why we reject our new hypothesis. So this is another approach that you don't need to use your calculator to solve. So just in case you don't have your calculator or in case you don't have a TI-84. Okay, next sample. So let's read some problems here. So in this example here, they don't give you like the exact distribution that you're looking for. So what should we put in our H0 then? So if again, the problem is not giving you anything, you just like equally divide that. So the entire distribution is always 100% and then divided by 4 categories, which is each one worth like 25%. And also if they don't mention about the significance level, then we just use 5%. And then let's make a table here with our observed counts and also with our expected counts. Okay, so the observed counts for the first group is 32. For the second group is 20, 16, and 12. And the expected count is by multiplying the total by the proportion. So the total in this case is 100 probably. Okay, so the total in this case is 80. So our expected count is going to use 80 to multiply 0.25, which is 20. So my expected counts are all 20. So definitely my expected counts are all greater than 5. So the large sample requirement satisfy. Let's check. And for independency, it's just like reasonable to assume that there's more than 800 like league players from 2009 to 2010 seasons. So just some reasonable assumption about the population. And then the do is going to be chi-square equals to observed minus expected, and then adding it all up. And now let's solve it. So again, go to stat and add it. So let's do 32, 20, 16, and 12. That L1 is our expected counts, and L2 is our observed. So they're all tiny. And then after you finish inputting the number, do a second mode and then go back to the home screen and go to stat, test, and then chi-square GOF. GOF means goodness of fit. And then now my degree of freedom is 4 minus 1, 3, because we total have like 4 categories. So our chi-square in this case is 11.2. And the P stands for p-value. And then now if we are just trying to find a p-value using like chi-square distribution, we can do a second var, go to chi-square CDF, and then 11.2, and infinity, and degree of freedom is 3. And then paste it. You can see that this p-value is the same as the one that we use, like the chi-square goodness of fit. So either way, you get the p-value. And then this is our p-value. And since our p-value is again less than 0.05, we reject the new hypothesis. And then we don't have any convincing evidence that at least one of the proportions for people born in each quarter of the year for the NHL is equal throughout the year. And now let's use our second approach, which means, let's say we lose our calculator or somehow we don't have our calculator. So the second approach is again, you got to do this by hand, and then find the critical value. For a significance level, and then the degree of freedom is 4 minus 1. 4 is because we have total 4 categories. So the degree of freedom is the number of categories minus 1. So the critical value in this case equals to, let's see, 7.81. Oh, and then I'm going to upload the chi-square table as well, like after the class. So you can use the table way to just check your answer. So now because our 11.2 is greater than 7.81, so that means we reject the new hypothesis. So that means we have convincing evidence that there is at least one of the proportion is not equals to 25%. So this is your second approach. Okay, now let's go continuous. Specifically. Okay. Next one, the chi-square test for homogeneous. And then for chi-square test for homogeneous, we're looking at what influence, what the column variables versus the row variables. And then compare the conditional distributions of column variables for each row variables. And calculate the conditional distributions among them. And then we will test for any distribution differences. And then if there are differences, analyze by the amount differences and by how much, or the actual differences by how much. And the aesthetic counts, it takes the marginal distribution for each row variables and multiply by total in each column variables. And then the degree of freedom is going to be row -1 times column -1. That is the degree of freedom, because now we're going to work on the matrix data. And then our H0 in this case is there is no difference in the distribution of the two column variables. And our HA is there is a difference. So remember our H0 is always no difference. So always equals to 0. And then again, large sample condition is the aesthetic count has to be greater than 5. And then the chi-square expected is observed minus expected over expected. And calculate the p-value with lower bounds, upper bounds, and degree of freedom. And then compare the p-value to the significance level. And then if the p-value is less than alpha, we reject the new hypothesis. And then if the p-value is not less than alpha, we fail to reject the new. We reject H0, so we do have convincing evidence. And then if we fail to reject H0, so we don't have convincing evidence. Okay, now let's do a test for homogeneous. So let's skip part A, which is just doing a bar graph. Now let's do the significance test. So we are curious if there is any differences in the distribution of superpowers for the kids from the UK and the kids from the US. So we are trying to see that if the column distributions are equals or not equals, or are they the same? So before we do that, we have to calculate the aesthetic counts for every single cells. So how to calculate aesthetic counts in a matrix setting is by multiplying the total and divided by the total for the first cell. So for the first cell, the column total is 200 times the row total, 99, over the total, 450. Which is 47.7. And then for the next one, it's going to be the column total, which is 215 times the row total, 99, over the total. Then let's move on. So this is 200 times 96 over 415. And this one is so there are all the aesthetic counts. And then we need to find it one by one and see if the aesthetic counts are all greater than 5. But definitely they will be. So take some time to calculate it. So the number are 51.3, 46.265, 49.735, 32.289, 34.711, 20.723, and okay. So those are the aesthetic counts. And then after we get all the aesthetic counts, we just need to check if all the aesthetic counts are greater than 5. Yep, they're all greater than 5. So large sample requirement satisfied because all the aesthetic counts are greater than 5. And then independent is just to make some reasonable assumption that there is more than 2,000 kids in US and that much kids in the UK. I mean, this is in the US and this is in the UK. And now it's really like doing the chi-square. So our chi-square is going to be observed minus expected. Wait a second, let me take a picture of this so I don't need to scroll back and. So 54 minus 47.7 square over 47.7 plus so you need to calculate all that numbers. So again, we can use calculator. So now let's take out your calculator. Let's learn how to do it on a calculator. Okay, now let's do second matrix because now all our data is in matrix. And go to edit. And then because we are going to put all the observed counts in our A matrix, so hit enter for the A matrix. I already did that, so it's going to be 5 by 2, and then input all the data as your observed counts. So take a few minutes to do this.
Sorry, we go to second what?
Or second matrix here. So second matrix. There's 2 keys, and then go to edit, and then hit matrix A. And after you finish, use second mode to go back to the home screen. And then again, go to stat, test. So for this one, you don't need to input your like observed counts. It will just calculate it by themselves, by the calculator. So go to chi-square test. So because now it's not like a sequence, not a list of data, it's a matrix. So you go to a chi-square test. And then telling them, yeah, I put my observed counts on A, and then please store the expected values on B, and just hit calculate. So now that is the chi-square. Like that is the sum for that gigantic equations. And then the P is the p-value. So the p-value for this one is 0.178. And again, if you want to double check that the p-value is really that number, go to second vars distribution and now just do a chi-square CDF again. And now your lower bound is going to be 6.2914154, and that's your upper bound's lower bound. And then what is your degree of freedom? So your degree of freedom now is the column, the number of total column minus 1 times the number of total rows minus 1. So total, I have 2 rows for UK and US. And the number of rows I have is 5. Like 5, freeze time, invisibility, super strength, and telepathy. So it's going to be 1 times 4, which is 4. And this is my p-value. Any questions on the calculator? Okay. So our p-value is 0.178. So because our p-value is greater than the 5% significance level, we failed to reject the new hypothesis. And then we don't have any convincing evidence that there is a difference in the distribution of superpowers for kids from the UK and the kids from the US. Oh yeah, one more thing. How do you find the expected counts on your calculator? I forgot that. So on your calculator, after you run the chi-square test, go to the second matrix now. And now you should have like something on your B matrix, like me. So this is the expected counts calculated by the calculator. So just hit B and then enter. Sorry, my phone freeze. Okay, here we go. So this is the expected counts. So you don't need to like calculate it one by one, but definitely you need to know how to do it, because I will ask you like what is the expected counts for like a certain values. So you will need to know exactly how you can get the expected counts, but calculator is just allow you to save some time. It's not doing everything for you. Okay, so now let's see if again you don't have your calculator with you, then what happened? So again, after you get the chi-square, go to the table. So the second approach. So for the second approach, you cannot calculate the p-value, but you can use your calculator to calculate this gigantic like matrix. That's possible, but just be careful. And this is the number that you're looking for. And now find a critical value with a significance level of 5%, and the degree of freedom is row minus 1 times column minus 1, which is the row minus 1. How many rows do you have? 5 in total. And how many columns do you have? 2 in total. Disregard the total, like don't count the total. And also when you plug into the calculator, don't count the total. You only care about like what happens in the matrix. This is where you need to plug it to your calculator. The total is only for you to calculate the expected counts. So don't count the total. And also don't put the total to your matrix in the calculator. So this is what you need to put in to your calculator. So now have total row equals to 5 and column equals to 2. So row minus 1 times column minus 1, 4 times 1, which is 4. So that's the degree of freedom that you are looking for. Then now go to our chi-square table. So again, the critical value is 9.49 with 5% significance level, and degree of freedom equals to 4. 9.49. So the critical value is 9.49. And unfortunately, our chi-square statistic is 6.29154, which is less than 9.49. So on the test next week, I will not ask you to find a p-value, but I might ask you to find a critical value. Because even though you have your calculator, but you are also responsible to know how to use a non-calculator way to find your answer. So I will ask for the critical value. Yes, question?
Yeah, Professor?
Yes.
Okay, for the test, you give you a time like last time, or we can take on time?
It's the same as last time. Like the test is during class, and then you open your camera and then log into your Zoom, and then I proctor there.
Yeah, because this like these two, like last homework and this one, so it's a little more like not complicated, but it's more like process to it. So that's why I'm ask you if he on time or you give you time to.
What do you mean, like on time? Like
No, I mean like on time is like because for my other classes, well, I know everyone has for different, but we only like assign the test, and we can, for example, you have it like the whole day to do it from 8 a.m. to 11:59 p.m. So
yeah, I will let you guys to decide. I will like set up a poll maybe on Canvas to see like if you guys like a whole day test or a test for like 1 hour and a half. But definitely the whole day test is going to be harder.
okay.
Yep. So if it's only like an hour test, then it's going to be easier, and then the problem is going to be shorter. But it's a whole day test, definitely you get more time, but it's going to be harder. And then I will set up a poll on Canvas and see like which one you guys prefer.
Okay, thank you.
Okay. And then the chi-square statistic is this because it's less than 9.49, which is less than the critical value. So that's why we fail to reject our new hypothesis. And we cannot say there is any differences between the distribution for the UK kids and the US kids. So this is the second approach. So on the test, I will not ask you to find a p-value because if you don't have DR84, it's impossible for you to find a p-value on only the table. But I will ask you how to find a critical value because you are responsible for learning like the second approach as well. So after the class, you forget how to use your calculator, you still have something left. like even using the table that you found online, and then you can do the significance test. And then I will put the poll like saying like what kind of test format you guys like. And then the poll is going to be due this Friday. It's optional. So if you want to express your opinion, then go for it. If not, then I will just decide it for you. I will see like which one has the majority for both class. Okay, so yep, that's it for today. And then I'm going to post the video like as soon as possible for today. And then, yep, if you have any questions, just email me. Okay, see you guys on Wednesday. Bye.